Today I'm going to talk broadband power meters and downstream PON power meters, as well as through mode PON power meters, help you understand the difference. So we'll start with a brief refresher of optical power and loss measurements and how we measure power and loss using a broadband optical power meter. A brief slide on PON architecture and its impact on making power and loss measurements, how we can measure power using a downstream PON power meter and how that's different from a broadband power meter, and then what makes a through mode PON power meter different again from a downstream PON power meter. And then we'll wrap up with power meter selection based on the application the user is trying to address and the relative cost of the various power meters. So optical power, that's an absolute measure of the power coming out of a fiber or coming out of an optical transmitter. It can be measured in watts or dBm, which is dB relative to 1 milliwatt. And dBm power is calculated as 10 times the log of the actual power in milliwatts divided by 1 milliwatt. An example here is if you measured a tenth of a milliwatt, then the 10 times the log of a tenth of a milliwatt over 1 milliwatt gives you a minus 10 dBm power reading. So optical loss, that's the difference in power, and it's measured in dB. We can measure the insertion loss of a network using a source and a power meter, where we inject power at a known level into one end of the network, and we measure the power coming out at the other end of the network, compute the difference, and that will give us the loss in dB, as long as the difference is being measured in dBm. We can compare that measured insertion loss to the loss budget to determine pass or fail. And then in the case of failure, in which the insertion loss exceeds the calculated loss budget, then we would want to try to identify the sources of excess loss that are causing the insertion loss to be too high. So dB loss, it's the output power minus the input power. In this case, our output power from our light source is minus 7.5 dBm. Our input power to our optical receiver is minus 29.2 dBm. And the difference between those is 21.7 dB. And that's our optical loss. Loss budget. How do we calculate our loss budget? Typical way to do that is take the number of connectors times the maximum allowed loss per connector, and a typical number there is either 0.5 dB or 0.75 dB. Add to that the number of splices times the maximum loss per splice, and a typical maximum loss per allowed loss per splice is 0.3 dB, although some service providers may have a tighter limit than that. Add to that the maximum loss per splitter if you're in a PON network that includes a splitter, and the maximum loss per the splitter will be dependent on the split ratio. And then finally add to that the total length of the fiber times the maximum loss per distance of that fiber. And a typical number for maximum loss per distance of the fiber is 0.5 dB allowed. Add those all together, and that will give you your loss budget in dB that you would compare to your measured insertion loss. In the case of a broadband optical power meter, it has a detector in it that is sensitive to a wide range of wavelengths. Just as our eyes can see all the colors in the visible spectrum, blue, red, green, yellow, purple, etc. The broadband optical power meter can see the different wavelengths of light used in optical communications, but it responds differently at each of those wavelengths. And the graph to the right shows you that the response at 1310 is a little bit lower than the response at 1550. Consequently, we calibrate the optical power meters at each of the wavelengths of interest. Power meter for single mode would be calibrated at 1310, probably at 1490, 1550, 1625, and 1650 nanometer. For multi-mode, we would also calibrate at 850 nanometers and 1300 nanometers. And you can see from that graph that 850, the responsivity is very different. When a single wavelength is present, the power meter user has to select the correct calibration factor. So you have to select 1310 if you're measuring 1310 nanometer light. If multiple wavelengths are present simultaneously, the power meter will actually measure the aggregate power. And the power meter can't tell what wavelength is present. Just as our eyes, when we see white light, we can't tell how much purple, how much red, how much green, how much blue. All we see is the total amount of white light. While measuring optical power with a broadband power meter, you would connect to the network for which you want to measure the output power, or you would connect to the transmitter for which you want to measure its output power. You would select on the power meter the wavelength to be measured. That's how you're selecting the appropriate calibration factor. And then you would view the measured power. Make sure that when you do that your measurement units are in dBm or watts, not dB. If you're displaying dB, then you're not measuring power, you're measuring loss relative to a reference stored inside the optical power meter. So here we see the display showing that minus 3 dBm output power at 1550 nanometer is measured correctly because we've selected the 1550 nanometer calibration factor. If we switched the calibration factor to 1310 nanometer, we see that we get an incorrect reading of minus 2.14 dBm. So how do you measure insertion loss or optical loss with a broadband power meter? Pretty simple process here. You would enable the source at the wavelengths to be tested. Handheld optical light source, I've shown it on the left there. You would connect the source to the power meter using a jumper or a launch cable. And then you would store the measured power on the OPM, on the power meter, as the 0 dB reference at the wavelengths to be tested. Now, in this case, we're using wave ID, which the optical light source will toggle between sending 1310 and 1550 nanometer. It's still sending only one wavelength at a time. The power meter automatically synchronizes. It knows when 1310 is being received and use the appropriate calibration factor for 1310. It knows when 1550 nanometer is being received and uses the appropriate calibration factor. And when you press the store reference, it will store references at each of those wavelengths based on the measured power at each wavelength. So now that we've referenced our power meter to our source, we can connect the source at one end of the network, take the power meter to the other end of the network, select the wavelengths to test on the light source and power meter, and view the measured loss in dB. Again, if at the light source we're using wave ID and we're sending 1310 and 1550 toggling back and forth, the power meter will automatically synchronize to that and measure the loss at each of those wavelengths. And here I've shown 1310 measuring a loss of 3.27 dB through the network and 1550 measuring a loss of 2.41 dB through the network. If you don't have wave ID in your source, then the user has to, manually select 1310 at the source. The user at the other end of the network has to manually select the 1310 calibration factor, make the measurement, let the guy at the source end know to switch to 1550, and then at the power meter, switch to 1550 and take the measurement. So obviously it takes longer, it's error prone. So wave ID allows them to make insertion loss measurements much more quickly and without the risk of setup errors. So let's talk briefly about passive optical network architecture. In this architecture, an optical line transmitter in the central office or the head end transmits downstream at 1490 nanometers, and it accepts 1310 nanometer upstream signals back from the ONT at each of the subscribers. The downstream broadcast goes to all homes, and each of the ONTs at each of the homes decodes only those signals destined for it. In the upstream direction, each of the ONTs is assigned a time slot by the OLT in which it may transmit. So only one ONT can transmit at a time, and that's how we prevent collisions in the upstream direction. For that reason, an ONT is not allowed to transmit in the upstream direction unless it is connected to an OLT and receiving communications from that OLT. Very important to understand that point. At the central office, it's possible that the service provider will overlay their GPON or EPON network with an RF video, a radio frequency video, that normally transmits downstream in the 1550 nanometer region. So now we would have two downstream wavelengths, 1490 and 1550. With bandwidth demands ever increasing, there are next generation PON technologies, and one that seems to be gaining the widest acceptance right now is XGS PON, which is 10 gig symmetric, 10 gigabit per second downstream, 10 gigabit per second upstream. But a lot of service providers have already deployed GPON. So in this case, they may overlay their GPON network with an XGS PON network, and they overlay it simply by wavelength division multiplexing together the new wavelengths added by XGS PON. So it broadcasts downstream using 1577 nanometers, and the upstream signals from the ONTs are transmitted at 1270 nanometers. And those wavelengths were chosen specifically so as not to interfere with the existing GPON wavelengths. And this allows that both GPON and XGS PON can coexist in a network. And the reason they may want to do this is they don't want to upgrade the ONTs at some of the residential houses, but they may want to add higher speed broadband services for businesses or for additional customers who are willing to pay for that higher speed. So now at the home, we have the possibility of three wavelengths coming downstream, 1490, 1550, and 1577. There's two wavelengths that only one wavelength will be transmitted upstream because the ONT won't simultaneously support GPON and XGS PON, but it may be transmitting upstream either at 1310 or 1270 nanometer. So as I mentioned before, the ONT is not allowed to speak unless it's spoken to by the OLT. And that's true for all of the PON architectures, GPON and EPON, as well as XGS PON. There are other 10 gig PON technologies as well. XG-PON is 10 gig PON asymmetric, so it's 10 gig downstream, but only 2.5 gig upstream. And then there's 10 gig EPON, but currently XGS PON seems to be the one that's gaining the most popularity. So downstream PON Power Meter, it's capable of monitoring downstream wavelengths only. To make a downstream PON power measurement, you would disconnect the drop cable from the ONT at the subscriber premise, and you would connect it to the PON Power Meter. In this case, you may have multiple wavelengths present. You may have the 1490 nanometer downstream, you might have 1550 RF video downstream, or you might have 1577 XGS PON downstream. In order to make the measurement, the broadband power meter would simply aggregate the power and give you one reading, and you wouldn't have no idea how much of that contribution is coming from the 1490 GPON, the 1550 RF video, or the 1577 XGS PON. A PON power meter will separate the wavelengths to individual detectors. So it has wavelength division demultiplexer built into it going to detectors. So the 1490 nanometer will be routed to one detector, the 1550 to another, 1577 may be routed to the same detector as the 1550, which is the case in our TS100, or it may be routed to a separate detector, which is the case in our Flow Scout. This allows, when simultaneous wavelengths are present, it allows the downstream PON power meter to independently monitor the 1490 nanometer GPON, the 1577 XGS PON, or the 1550 RF video. The PON power meter will compare the measured power levels to the minimum and maximum allowed at each wavelength. So the GPON and XGS PON standards were developed by ITU-T, and those standards include the minimum required and the maximum allowed levels 4G PON and XGS PON at the subscriber's ONT. It also specifies the minimum and maximum output power at the OLT. Then that's again in the downstream. IEEE is the source of the EPON and the 10 gig EPON standards, and they also include specifications for minimum and maximum levels. It's not unusual for service providers to modify the minimum and maximum limits based on their requirements. They may have equipment from a vendor that exceeds the minimum requirements of the ITU standard, and so they may modify their limits accordingly. There's also multiple classes output power specified in the standards, and so they may need to adjust their limits based on the class of transmitter that they're using. So once you've selected your limits, then the measured power is compared to that limit, those limits, and a pass-fail indication will be shown. So here I've shown the TS100 PON Power Meter display. When you connect to the drop cable and you initiate a test, it will immediately measure the downstream RX power. In this case, we see that we're receiving minus 9.1 dBm at 1490 nanometer, and that's within the passing level. And we see that we're not seeing any light at 1550 and 1577. And in this case, we were configured to expect light in that wavelength band, and we're not receiving any, so that's a fail. If you're not expecting any, if it's a GPON only network, you can disable pass-fail checking for the 1550 and the 1577. We'll still attempt to measure it and indicate if there's no light there, it would indicate less than minus 50 dBm, but it would be reported in a black color, not a red color, and there would be no red X there indicating a failure. So if your power levels are too high or too low, what to do about it? Well, in the case that the power level is too high, then you want to insert an inline attenuator, and the service provider would probably have, in his bag of tricks, fixed attenuators at various levels, and they would want to put in enough attenuation to bring the power level down to the point where it's within the maximum allowed signal level. If the downstream signal that you expect is absent or too low, then your course of action would be to troubleshoot upstream towards the OLT to locate the sources of excess loss. And the TS100 includes a built-in PON troubleshooter. We don't call it an OTDR, but it uses OTDR technology to test upstream, and it will display a link map of each of the detected connectors, splices. It will test to the splitter. And we have two models, the -60 that will test to the splitter but not through the splitter, and the -70 which will test through the splitter but not beyond the splitter, just so it can measure the loss of that splitter and compare it to min-max levels. So how does a through-mode PON power meter differ from a downstream PON power meter? As I'd mentioned, the ONT is not allowed to transmit if it's not connected to the OLT or it's not receiving a signal from the OLT. That means that you can only test the upstream signal levels when the ONT is connected to the OLT. So you can't just disconnect the drop cable from the OLT and connect a jumper from the ONT to your power meter and try to measure that upstream 1310 or 1270, because the ONT won't transmit. What you have to do is you have to pass the signal through your PON power meter so that there's an optical path that goes from the OLT to the ONT and from the ONT back to the OLT. And as you pass that signal through your PON power meter, you tap off a small amount of light in each direction, enough so that you can make upstream and downstream power measurements, but not so much that you would disrupt service to the ONT or disrupt the return signals going back to the OLT. Again, the PON power meter must be capable of separating the various wavelengths to individual detectors so that accurate power measurements can be made at each of the wavelengths. And that's true in both the downstream direction, where you may have that 1490, 1550, and 1577 present, as well as in the upstream direction. Depending on where you're testing, you may have both 1270 and 1310 nanometer present. Just as the ITU and IEEE specified min-max levels for the downstream signals, they also do that for the upstream signals. So in this case, I've shown an example of the Flow Scout through mode PON power meter display. Here we see that the upstream signal at 1310 is out of spec, it's too low, and so it's failed, whereas the downstream signals at 1490 and 1550 are good. We know that at the point where we've inserted our PON power meter, we have acceptable downstream signal levels, but we're not getting an acceptable signal from in the upstream direction from the ONT. If we're connected right at the ONT, we would suspect a bad ONT and we would replace it. If we're upstream from the ONT, let's say we're at the splitter outputs, we may wish to troubleshoot in the downstream direction towards the ONT to determine the source of any excess losses in that direction. Now, the through mode PON power meter itself doesn't include a troubleshooting capability. It doesn't have an OTDR built into it or a troubleshooter built into it that will allow you to scan downstream and get a view of the network. So here again, you may choose to take your TS100 PON troubleshooter and disconnect your Flow Scout through mode PON power meter, connect your TS100 in the downstream direction towards the ONT, and test the network in that direction. In that case, it's a point-to-point network, so you would configure your TS100 for a point-to-point test, and you would expect to, see any connectors or splices between your test location and the ONT and attempt to identify those which are causing excess loss. So a summary here, when to use which type of power meter and what are AFL's solutions for that. Use a broadband power meter when you want to measure the transmit output power or the receive input power at a single wavelength, or if you want to measure optical insertion loss at one or more wavelengths. And again, using Wave ID, you can reduce test time and eliminate setup errors. For FTTH applications, the OLS7 FTTH and the OPM4 or 5 will allow you to measure at 1310, 1490, and 1550. And FlexScan FS200 series products, as well as the FS300 series products, they each include a broadband power meter. So the OPM4 and 5, that includes a broadband power meter as well. You can use a downstream PON power meter to verify the downstream power levels before connecting and activating your ONT. Once a network's been brought into service, if the ONT is not responding to the OLT, you can verify downstream power levels again at the ONT. You could also verify them at the output of the splitter or anywhere between the OLT and the ONT. The expected power levels will be much lower after the splitter because of the high loss through the splitters. If the power levels are okay, but the ONT is not responding, then your solution is to replace the ONT. There are no user adjustable parts on the ONT, so there's nothing that the installer can do to, I'll say, fix an ONT that's not responding. So his only solution is to replace it. If the power levels are absent or too low, then as I mentioned before, you would troubleshoot upstream from the ONT using the troubleshooter capability built directly into the TS100. So use a through mode PON power meter when you want to verify both the upstream and the downstream levels before activating the ONT. And again, if the ONT is not responding to the OLT, you can use this troubleshoot at least to the point of determining at the point where you've inserted the Flow Scout, do I have downstream power at adequate levels and my signals are okay in that direction and the problem is just in the upstream direction, or do I not have adequate signal levels reaching the ONT? Based on that, you would make your troubleshooting decisions. If the power levels in the downstream direction are okay, but the ONT is not responding, then you would replace the ONT. If the downstream power is absent or too low, you'll troubleshoot upstream from that point towards the OLT. And if your upstream power is absent or too low, if you're right at the ONT, then replace the ONT. If you're upstream from the ONT, then you would troubleshoot downstream towards the ONT. So wrapping up here with a quick summary, my goal here was to help you understand the difference between broadband and PON power meters, help you to understand the difference between what a downstream PON power meter and a through mode PON power meter are capable of doing, help you, if you had any confusion, to measure power in dBm or watts using a broadband power meter or a PON power meter, and measure insertion loss, again in dB, using a light source and an optical power meter. You can verify PON power levels using a PON power meter when multiple wavelengths are present simultaneously, whereas a broadband power meter cannot give you adequate measurement when multiple wavelengths are there simultaneously. Power meters can indicate a pass-fail. They can't troubleshoot that if you fail, though. OTDRs and troubleshooters such as the FS200 and the TS100 can help you identify and locate the source of failures when your power meters indicate power levels are too low. Some common mistakes to avoid when measuring optical power or loss: make sure that you've got your wavelength calibration factor set correctly. In the PON power meters, you don't need to select the wavelength since it automatically separates the wavelengths and reports that at each. But in a broadband power meter, you do have to do that unless you're using wave ID mode. Make sure that your stored reference for loss measurements is correct. The way you do that is by referencing your power meter to your source before you go to make your insertion loss measurements. And don't attempt to use a broadband power meter when multiple PON wavelengths are present simultaneously. And then lastly, from the previous slide, know which AFL products provide which type of power meter. For broadband power meters, your handheld OPM 4 or 5 and the CSM families, as well as the FlexScan FS200 and FS300 families. Downstream PON power meter is included in the TS100-6070 with the P2 option, and that product also includes an integrated PON troubleshooter. And then the through mode PON power meter, the brand new FlowScout TPPM-XG. And with that, I'll wrap up.